Hello class, today we're going to go over Unit 2, Lesson number 1. This is going to be 2.1, Determining the Average Rate of Change. In other words, this is called AROC, okay, because later we're going to do something else called Instantaneous Rate of Change. Today's lesson is usually well received, and that's because basically when you calculate rate of change, that should be making you think of grade 9 when you kind of first heard about it. Rate of change is another way of saying slope. So the slope between any 2 points. And we were used to doing a slope of a line. So today what we're essentially doing, even though we've got a fancy kind of new word, average rate of change, and then later instantaneous rate of change, I just want you to know that all we're doing is calculating slope. Okay? So what are we calculating the slope of, though, if we're not always just dealing with straight lines? How do slopes pertain to shapes that are not linear? So this will have to do with what we call a secant line. So a secant line is a line that passes through 2 points on the graph of a relation. Okay? So for example, we've got a parabola here, and then there's the points PQ on the parabola. And if we were to draw a line that connects through PQ, then we would say that this is a secant line. So here in red is a secant line. And then we would, if we wanted to find the slope of it, it would be that we would find the slope of PQ. Okay. All right, so the average rate of change, or AROC, is the change in the quantity represented by the dependent variable divided by the corresponding change in the quantity represented by the independent variable. Right, so it's always change in y over change in x. Okay. So algebraically, the average rate of change for any function, so if I give you an equation of a function, so f of x equals, and I give you the equation, and then I ask you for the average rate of change over a given interval. So say, I give you one x value, x1, and then I say, and I want you to tell me what the average rate of change is from x1 to x2. So all you have to do in that case is, we know that average rate of change is change in y over change in x. Okay, so usually that's written, you might see it more in science, as delta y over delta x. And if I give you an equation over this interval, what you're going to do is you're going to have to first find the y values, the difference in the y values over the interval. So you're going to sub in the largest of the x coordinates of the interval. So you're going to do f at x2 minus f at x1. Okay. And then you're going to divide it by the change in the x's, which is x2 minus x1. Okay, so you're going to do that when you have an equation. Okay. Okay, and then they give the interval here. All right, so that's how you can do it algebraically. Graphically, so sometimes I might give you a graph and then you have to visually see what the 2 points are. So maybe there's no equation given. The average rate of change for any function over the interval, same as before, but it's going to be equivalent to the slope of the secant line. So for example, you're going to pick the 2 points, or whatever the question's asking for. You're going to draw your straight line through the 2. Right, so this is the secant line here. That's passing through x1, y1 and x2, y2, whatever the question asked. So the average rate of change is equal to the slope of the secant. So that's just slope symbol and subscript secant. Okay, which we know is change in y over change in x. And then when you're just given 2 coordinates, you're just going to do your regular slope formula from grade 9. So y2 minus y1 divided by x2 minus x1. So remember, average rate of change is always expressed using the units of the 2 quantities from the change in the dependent and the change in the independent. So for example, that's why sometimes if it's a word problem, when you calculate average rate of change, for example, and you're comparing distance over time, your final answer would be 20 kilometers per hour as your rate of change. Okay, so it should always have the 2 quantities. All right, so if I drew a secant line, for example, here on this side of the parabola, okay, I already know that just by looking at it, that the slope of that secant line, if I calculated it, would be positive, and that's because it's rising to the right. So you're going to get a positive average rate of change, and that will indicate that the quantity represented by the dependent variable is increasing on the specific interval, okay, compared with the quantity of the independent. So graphically, this is indicated by a secant line that has a positive slope and therefore is rising from left to right. Okay. A negative rate of change would obviously be the opposite. So here we've got another interestingly shaped graph. So if we took a secant line, if we found the slope of this secant line here going through these 2 points, we can see that over this time the dependent variable is decreasing on this interval as the x is increasing. So graphically we can see this secant line has a negative slope, and therefore the secant line, that's why it's falling from left to right. Okay, so when we calculate the average rate of change here, it should be negative. And obviously from what grade 9 we did, all linear relationships have a constant rate of change. Okay. So the average rate of change calculations overall, any intervals on a linear relationship will always give you the same results, the same number back, right? So if we had said Sarah rents a car from a rental company, what is the average rate of change in the rental cost for 0 to 100 kilometers driven? Okay, so again, always giving you some sort of range here. So 0 to 100 kilometers, you'd go to your graph, you'd highlight the point here, so 0 and 35, that you'd highlight the point when x was 100, so it's 100, 50, and then you do that the AROC was equal to y2 minus y1 over x2 minus x1, okay, and that would leave us with, so remember labeling, so x1, y1, x2, y2. Okay, so 50 minus 35 over 100 minus 0, and we can see that we get 15 over 100, and in this scenario that'd be 0.15. And we know that no matter what here, if I picked any 2 other points on this line and I asked you for any other interval, so maybe I said from, you know, a 150 to 200, what was the average rate of change, you would actually only have to do ever this one calculation, and then you'd say because it's linear, it's a constant AROC, and therefore it will be the same value as the one you calculated. So the average rate of change in rental cost is 15 cents per kilometer. So remember, word problem, make sure you have the 2 units of measure. Okay, so the dollars and the kilometer. Okay. All right, now obviously we're going to focus on a bit more non-linear relationships, and those do not have a constant rate of change, we know that. So the average rate of change in calculations over different intervals are actually going to give us different results, and then those different results we're going to analyze. So we're going to determine the average rate of change for every unit for the function f of x equals 2 to the x from 0 to 3. Okay, so every unit. Every unit means a length of 1. So let's start off, let's do from 0 to 1. So I know it's kind of hard to see that here, but here in black, I've drawn my secant line from 0 to 1, right? And I know right now it kind of looks like it's matching the graph perfectly, but remember this is an exponential graph, so this graph here is never linear, okay? You can zoom really close up to it and it would look linear, but when you pan back, it's actually never increasing by a constant rate. So let's find the AROC from 0 to 1. Okay, so if you want, you can just sub the 1 and the 0 into the equation, or you can go to the graph and see what the number is there too. Okay, so you have both options. So it's going to be f at 1 minus f at 0 all over 1 minus 0. So that's 2 to the 1 minus 2 to the 0 divided by 1 minus 0. 2 minus 1 divided by 1. And that leaves us with a AROC of 1. Notice it's not a word problem, so we can't really put a unit per unit. So we're just reading this as 1. All right, now let's draw the secant line from 1 to 2. So have a straight line, a straight edge there to do that. And we're going to find the slope of that blue line. So f at 2 minus f at 1 over 2 minus 1. So that's 2 to the 2 minus 2 to the 1 over 2 minus 1. And that leaves us with an average rate of change of 2. And now we'll do the slope of the secant line from 2 to 3. So we're finding the slope of this secant line here. Just keep in mind, the secant lines can keep going further and further, so you can extend these. You don't have to stop them like just kind of the way I did there. Obviously, secant lines can keep going and going. All right, so f at 3 minus f at 2 all over 3 minus 2 will leave us with 8 minus 4 divided by 3 minus 2, so that will leave us with 4. So notice that the average rates of change are all increasing. Okay, and that makes sense. You could have predicted, you may not have predicted these exact numbers, but you should have been able to predict that the average rate of change was going to be a different number each time. One, because you knew it was exponential and not linear. You should have predicted that all the AROCs were going to be positive, and that's because when you drew all these secant lines, they were all rising to the right, so that means a positive slope. And the third thing you should have been able to predict was that as you calculate the AROCs moving forward, that the numbers of the AROCs should have been getting larger. And that's because the steeper the line, the larger the slope. And keep in mind, it's always the larger the absolute value of the slope. So if you were dealing with negative numbers too, you would make sure you look at the positive version of the number to see if it's larger or not. So we can see here, the steeper the secant line means the larger the AROC. So we can see the red was steeper than the blue and our purple here, which I just have in the black for now. We can see that, so we knew this was going to be a larger value, and it was, right? It went from 1 to 2 to 4. Okay, so the slopes of the secants will keep getting larger and always positive. So if I kept going and going, the numbers are going to get even larger and larger, and they're still going to be positive because the graph, this exponential graph, is always increasing. Okay, so always increasing. Okay. All right, it says Andrew drains the water from a hot tub. The tub holds 1,600 liters of water. It takes 2 hours for the water to drain completely. The volume in liters of water remaining in the tub at various times t in minutes is shown in the table and the graph. Okay, so you can choose to get your point specifically from here or just reference it from the table. All right, so it says calculate the average rate of change in volume during each of these different time intervals. So just so you know, every time you do that, make sure you draw your secant line. Okay, so if we have to do the average rate of change from 30 to 90, that would be, so go to 30, that's 1, and then 90, that's your secant line. And like I said, you can extend this. It doesn't have to stop right at the, it doesn't have to be a line segment stopping right at those points, okay? All right, so we're going to do volume of 90 at 90 minus volume at 30 divided by 90 minus 30. Okay, you can go to the table there. You just get negative 800 divided by 60, which rounds to about negative 13.3. And it's a word problem with units, so liters per minute. Okay, so when you give your therefore statement, the average rate of change will always have a sign, so it'll always be plus or minus, and then I'll obviously always have the number with it. So I always want you to interpret in terms of the word problem what the positive or negative means, and then along with the, obviously taking into consideration the absolute value of the number itself. So what would you say here? You would say from the 30th minute to the 90th minute, the volume is decreasing, so the decreasing takes care of the negative, at a rate of 13.3 liters per minute. All right, from 60 to 90. Okay, volume at 90 minus volume at 60 divided by 90 minus 60. This leaves us with negative 10 liters per minute. So the volume is still decreasing because it's a negative AROC, but it's decreasing at a rate of 10 liters per minute. Okay. So if we were to compare the slopes of these two, remember when you compare steepness, you ignore the sign, so you always just got the absolute value of the number. So this is steeper than this. Okay, and you can see that even here, the slope of the blue secant line is much steeper than the slope of the green, so we already knew that they both should have been negative, but this one here should have been a larger negative, this one a smaller negative. From 90 to 110, so that's our little purple one here. When you calculate volume at 110 minus volume 90 over 110 minus 90, we should get negative 4.5 liters per minute. So the volume is decreasing at a rate of 4.5 liters per minute. Again, much smaller AROC value and still negative. And from 110 to 120, we get an AROC of negative 1 liter per minute, so the volume is decreasing at a rate of 1 liter per minute. So why is the rate of change in volume negative during each of these time intervals? And that's because the volume is always decreasing as time passes, so it never mentions where the bathtub is being filled back up. Does the hot tub drain at a constant rate? Explain. Based on our calculations here, definitely not. We didn't get any of the same numbers. No, since the AROCs are all different values, therefore non-linear. Okay, so obviously we can see that from the graph, but a lot of this unit is how can we take calculations of numbers? So how can we take AROCs to make conclusions, sometimes like without the graph? All right, also something else that you should notice here is the absolute values of the AROCs. Okay, so as you go over time and time, I know all these intervals aren't the same amount, but as you get closer to the bottom, okay, you should notice that the absolute values of the AROCs are getting smaller. 13.3, 10, 4.5, 1. And remember, absolute value means the positive version. So why do you think that was happening? Okay, so why is it changing in terms of this scenario? And that's because the water pressure was larger, okay, at the start, and that's because there was more water present in the tub. So there was all that water pressure pushing down, making the water drain faster, compared to later on when there's less water in the tub, so there's less pressure on the water, so it's not draining as fast. So therefore we can conclude that it was draining at a faster rate in the beginning, based on our AROC calculations. All right, and our last example here says a rock is tossed upwards from a cliff that is 120 meters above the water. The height of the rock above the water is modeled by this quadratic equation here, where h is the height, h of t in meters, and t is time in seconds. Okay, so again, I don't just want you to try to do factoring methods to kind of answer this or visualize this. The whole point of this unit is that you use rates of change in order to determine shapes of graphs and answer questions. So, I mean, obviously at the side, you can use like your factoring strategies maybe to, confirm what your ideas are. But this is mainly what I want to see in Unit 2. So it says calculate the average rate of change in height during each of the time intervals, and then we're going to make conclusions about the rock and what we know based on this. All right, so for this one, we're only given an equation, so we have to use the equation. Okay, no graph. So we're going to go from 0 to 1 second. Okay, so h at 1 minus h at 0. Okay, remember that one's always first. All over 1 minus 0. So when you sub that into your equation, okay, you get 125 minus 120 divided by 1, and that leaves us with 5 meters per second. So I want you to analyze what that means, right? Because I know you guys can enter numbers into a calculator, but if you don't know what the number represents, then all of this isn't useful. Okay, so that means the rock's height is increasing at a rate of 5 meters per second. Okay, increasing because the number is positive. So we know over this interval that the rock is still rising. From 1 to 2 seconds. So h at 2 minus h at 1 all over 2 minus 1. That leaves us with -5 meters per second. So for over this time period, the rock's height is decreasing at a rate of 5 meters per second. Okay. You can even say at a rate, or you can say at a speed of, if you'd like to as well. 2 to 3 seconds. When we sub that in, h at 3 minus h at 2 over 3 minus 2, we get -15 meters per second. So now the rock's height is decreasing at a rate of 15 meters per second. And then from 3 to 4 seconds, we get a AROC of -25 meters per second. So now the rock's height is decreasing at a rate of 25 meters per second. So remember, decreasing said with negative, increasing said with positive. Okay, so let's answer part B. It says, as time increases, what do you notice about the average rate of change in height over each 1 second interval, and what does it tell you about the graph and what's happening? So let's answer that with 3 points. Okay, I do take up space into the next question. So we'll just answer part C quickly here. It says, describe what the average rate of change means in this situation. So what it is really telling us what the velocity, so velocity is speed and direction. So it tells us the velocity of the rock as it's rising or falling, right? So how fast it's moving. So basically the rocks change in height over time. So just if I gave you these numbers, what are the conclusions that you can make? Conclusion number 1. Since the AROCs change from positive to negative values, this indicates that a turning point occurred somewhere in between. Okay, so that means a maximum is reached in between 0 to 2 seconds. Okay, and that's because, look from here, from 0 to 1 it was a positive, and then from 1 to 2 it was a negative. So all we can conclude from that is that there was a turning point somewhere, and it occurred somewhere between 0 to 2 seconds, right? And that's because the height was increasing and then it was decreasing. All right, let's see, can we be even more specific? So now what if we analyze the absolute values of the AROCs from 0 to 1 and 1 to 2? If I look at the absolute value of these two, they're the same. Their speeds are 5 meters per second, 5 meters per second. One is just increasing, one's decreasing. So one's rising, one's falling. So since the absolute values of the AROCs over those two intervals are the same, and since we know it's a parabola based on its equation, so we know parabolas are symmetrical, then the only way that you could have two slopes that are the same absolute value but different signs, it indicates that the max was reached right in between. So it was reached right in between 0 to 2, so right at the 1 second mark. So this is why I have a diagram up here. Right, so we have our blue parabola. Okay, the slope of the secant line from 0 to 1, right, should have the same absolute value as the slope from 1 to 2. So the only way they can have the same and be symmetrical is if there was a max reached right here in the middle. Okay. And that's something we could only conclude because of the absolute values being the same on left to right. Okay, and knowing what we know about parabolas. All right, there's actually even more that we can discuss about this scenario. So look what happens after it reaches its max. We have -5, -15, -25. So what can we describe about that? What do we know? We can also conclude that since the absolute values of the AROCs after the max are getting larger, so that's true. So if I took the absolute value of this, 5, here it's 15, here it's 25. So the absolute value of the AROCs are getting larger. It indicates that the rock is falling at a faster rate or a faster speed as it gets closer to the ground. And that makes sense, right? If you have something in the air and you drop it out of your hand, when it first leaves your hand, it's not falling at such a fast rate as it is when it gets closer and closer to the ground, because due to gravity, it's pushing it further down. So that's why these rates, these absolute values are larger. So it's just confirming to us that the ball, sorry, not the ball, the rock is getting closer and closer to the ground. Okay, and picking up speed. All right, and that was average rate of change. Hopefully everyone enjoyed that. Just remember, it's just another fancy way of saying that they want you to calculate the slope between 2 points on a graph. Okay. All right, make sure you try as much as the homework as you can, and let me know if you have any questions. Good luck.